Small sample hypothesis testing. Example 3a, in a sample of n equals 3 patients, proportion cured by new drug, p hat, 2 out of 3. 2 divided by 3 is approximately 0.67. 0.66 in repeating sixes, but approximately 0.67. It's known that the proportion cured by the old drug, p is 0.6, and the proportion not cured by the old drug would be 1 minus 0.6, would be 0.4. We want to test whether p equals 0.6, the new drug is not better than the old, versus p greater than 0.6, the new drug is better than the old. So if this is a right-tailed test, we're only going to think the new drug is better if in the long run the proportion cured is more than 0.6. So we want to check whether n times p0 is at least 5. So n is 3, p0 is 0.6, 3 times 0.6 is 1.8, and it's not bigger than 5, okay? And n times q0, 3 times 0.4 is 1.2, it's also not greater than 5. So these are no. Even if we had, we need 2 yeses here. If we have 2 no's or yes and a no, that means there's not, our sample is too small and we need to use the exact probabilities. We can't use the z-table. And the next step is to make a tree diagram, and we make the tree diagram as if h naught is true. Okay, so each patient is either cured or not, and they have if h naught is true, they have a 0.6 chance of being cured, a 0.4 chance of not being cured. The top path, we have all 3 patients that are cured. That's 0.6 times 0.6 times 0.6. I think 0.216. That's 2 cured and 1 not. And then we have next path, we have 0.6 times 0.6 times 0.4. I think it's 144. And that would be, oh, I'm sorry, this top path is all 3 are cured. I don't know why I did that. All 3 are cured. Here we have 2 cured and 1 not. The last one is not cured. And then we have, next path we have cured, not cured, and then cured. One, 4, 4. Cured, not, and cured. Okay, and then we have a cured and 2 not. And we can actually skip that path there. We only need the paths with at least 2 of the 3 were cured. So we can skip this path here. And not cured, cured. 0.4 times 0.6 times 0.6, 0.144. Not and 2 cured. And we can skip the rest of these paths. We only need the paths where at least 2 of the 3 were cured. So if we add those up, we get a p-value of 0.648. Okay, so that's not enough evidence to reject H0. Our p-value is more than alpha, so we've not enough evidence. We can also write these in a table instead of a tree. If you're using Pearson MyLab, they don't have capability for a tree, but they do have tables, and so we only need to list the paths where at least 2 of the 3 were cured, and so we have the third person not cured, the second person not cured. The one that's missing is the first one not cured. So we have not cured, and you have to use the same format that they're using with the initial capitalization and slashes in between each one. So that's the missing path. And that's going to be 0.4 times 0.6 times 0.6, 0.144. And add those up to get the p-value of 0.648. And that's more than our level of doubt, more than 0.05. So that means we failed to reject H0. The sample does not provide enough evidence to say that the new drug is better. Point alpha is equal 0.05 is a common level of doubt, but some researchers will use 0.1 or 0.01, or other researchers might simply report a p-value without specifying a level of doubt. So this table kind of helps us to interpret the p-value. So our p-value at 0.6 is between 0.1 and 1, so that means the sample provides little evidence that the new drug is better. So our p-value is between 0.1 and 1. So it's a little evidence. So our p-value here in this case. And then just some comments about the terminology. For possible outcomes, H0 is true, we don't reject H0. H0 is true, we reject H0. H1 is true. Some books use HA, it means the same thing. H1 is true and we don't reject H0, or H0 is true and we reject H0. So 2 of these are errors. If H0 is true and we reject H0, that's called a type 1 error. If H1 is true and we don't reject H0, that's called a type 2 error. So either way, you take a chance of making some type of error. In this case, we failed to reject H0, so that means we took a chance of making a type 2 error. So possibly a type 2 error here. We might have made a type 2 error. So 1 minus alpha is our level of confidence. The Greek letter alpha is our desired level of significance. I like to call it the level of doubt. It's a probability of a type 1 error. P-value is our actual level of doubt. That's what we computed here. We had a p-value of 0.6 something. The probability of a type 2 error, represented by the Greek letter beta, is usually not computed. We will not be computing beta, and it's usually not computed. You need to make some additional assumptions in order to compute beta. 1 minus beta is called the power of the test. Okay, so example 3b, we do example 3a, if the proportion cured by the new drug p hat is 1 out of 3, 0.33, we can use the same tree, but now we add the probability for all the paths with at least one cured, and I put these in red, so there's even more paths with at least one cured, and we have a bigger, even bigger p-value. So there's even weaker evidence that the new drug is better than the old. P-value of 0.936. Total of these paths in red here. Just the ones in red is 0.936 is our p-value. It's even bigger than our previous p-value, so even weaker evidence. And example 3c, if the proportion cured, if all three were cured, so then we have only one path. So it's a stronger evidence, but it's still not strong enough to reject H naught. We have the one path, 0.6 times 0.6 times 0.6, where all three were cured. We get 0.216, and that's still not enough evidence to reject H naught. And that concludes this presentation.